All right. Hello, everybody. We're going to wrap up section 7.2 with part 3 here, talking about properties of gases and the gas laws. All right. So we've made our way through 3 simple relationships. And we say simple because we're looking at 2 variables holding the other 2 constant. So PV, VT, and PT, right? So all of these options. Now, we notice that the same variables show up again and again. So we can actually combine these into a single equation, right? So if we look at volume and temperature, we have a relationship, and volume is also proportional to 1 over P. Now, proportionality just means that they change, right, together one way or another. And if V is proportional to both of these things, we can simply combine that and say V is proportional to T over P. And just by convention, we can rewrite this and put PV together and say the product P times V is proportional to temperature. And then we can say, well, actually, then if we divide by temperature, what we will end up with is a constant, right? It's equal to a constant. So if any set of PV and T for a given constant N, PV over T will always be equal to a constant. So if 2 things are equal to the same number, then they're also equal to each other, right? And we end up with the combined gas law, P1 V1 over T1 equals P2 V2 over T2. And notice, right, that the past are contained within here, right? These are all contained within here. And sorry, I in 1, F could be 2. It just means like initial and final, or first and second. Okay. All right, so let's test it out. Let's see what happens if we change more than just one thing or 2 things, right? All the previous questions, we held 2 constant. And now we're going to see if we allow pressure, volume, and temperature all to change, then what? And we're going to approach this the same way. So we have at a pressure of 4.2 atmospheres and 11 degrees Celsius. I'm just going to say right now that that's, if we add 273 to that, 284 Kelvin. A nitrogen bubble in the skin of a diver has a volume of 0.01 milliliters. What will the volume be when the diver ascends to sea level at 29 degrees Celsius? Okay, so we're going to add 273 to that, and we would get, let's see, 302. All right, so P1 is 4.2 atmospheres. V1, 0.01 milliliters. T1, 284. Okay, and then P2. What is P2? Okay, well, it's not given in the question, but it says the diver ascends to sea level, and the pressure at sea level is 1 atmosphere. Excuse me. T2, 302 K, and V2 is question mark. Okay. And the volume here is given in milliliters, so whatever answer we get out will be in milliliters. So P1 V1 over T1 equals P2 V2 over T2, and we're solving for V2. So we can multiply both sides by T2 and divide both sides by P2, and we get volume. And then we simply plug in our numbers. So 4.2 atmospheres, 0.01 milliliter, 302 K, T1 is 284 K, and P2 is 1. And we can see atmospheres cancels, Kelvin cancels, and we're left with milliliters, and we should get 0.045 milliliters. So the volume went up. Let's see if that makes sense. Right, the pressure went down, which would cause the volume to go up, and the temperature went up, which would also cause the volume to go up. So both of those indicate, yes, it should go up. And here's all of that a little bit nicer. Okay, now there's another relationship that we kind of skipped over that we're going to come back to. And this is the volume-mole relationships, right? Volume and N. And this one, I think we know, right? Here's a question. If you blow more air into a balloon, what happens to the volume, right? Obviously, it gets bigger because you're putting more air into it, meaning you're putting more gas particles, you're increasing the moles. So to express this in a similar way that we've done already, we say Avogadro's law tells us that volume is directly proportional to the number of moles. So here we see the picture where we can put gas in. If there's 1 mole of gas, we have a certain volume. If 2 moles of gas, we double the moles, we double the volume. So, if they're proportional to each other, again, then that means the ratio is proportional to a constant. And so any combination of V and N at constant pressure and temperature will result in a directly linear relationship. 1.5 moles of neon gas occupy a volume of 33.6 liters. What is the new volume after adding 0.5 additional moles of neon at constant temperature and pressure? Okay, so N1 is 1.5 moles. V1 is 33.6 liters. N2, it says we're going to add 0.5 moles. So now we'll have 2 moles. And what is the volume? All right, so we go to our equation. Going to solve for V2. We can do that by multiplying by N2. And plugging in. So the initial volume is 33.6 liters. We have 2 moles over 1.5. Right? So if we increase moles, we should expect volume to go up. And this ratio right here is telling us, yes, it will go up. So plug these into your calculator and we will get 44.8 liters. All right, here's that work, a little bit cleaner. And yes, it does pass what we expect. Okay, so we had the combined gas law, but even then we still assumed the number of moles was constant. Now, if we allow that property to change, we can add it to our list of ratios here, or proportions. So now these 3 can combine to give us volume proportional to NT over P. And in order to make that proportionality turn into an equality, we have to just have a constant. And so it's R. And R can actually be found if you have a gas where you can measure PV and NT, then PV over NT must equal R. And that turns out to be 0.08206. And the units on that would be strange, but bear with me, liters, atmospheres per mole Kelvin. Because nothing cancels out, they're all still there. That's what's needed to make this work. So this is universal, applies to every gas, and it is a constant. This is called the ideal gas law. And it's great because the ideal gas law contains all of the simple laws that we've just been discussing, right? If we just hold some of the variables constant, we end up with the simpler cases. So it's a very general case that applies to all gases. This is quite nice. This is a very good summary slide right here for you. All right, let's do a problem with this. Let's calculate the volume of 1 mole of gas in a beach ball inflated to a total pressure of 1 atmosphere at 0 degrees Celsius. All right, so we have 1 mole, pressure is 1 atmosphere, temperature is 273 K. We're solving for volume. Okay, so we have 3 values here and 1 unknown. Notice we're not changing something. It's not one of the other laws. This is just simply like a static picture of a gas. And so we will use the ideal gas law and solve for V. And we'll plug in what we know. 1 mole times 0.08206 liters times atmospheres per mole Kelvin times 273 Kelvin over 1 atmosphere. So the R universal gas constant helps with the units. So moles cancels out, Kelvin cancels out, atmospheres cancels out, and we'll be left with liters. We get 22.4 liters. Now, wait a minute. It just says gas. Does the gas matter? No, it does not. This applies to any and all gases. And actually, if we look at what we just did, we found 1 mole at standard pressure, and 0 degrees Celsius is considered standard temperature. And so we found the molar volume, right, the mole of one gas, at standard temperature and pressure. So this value of 22.4 is a common known value. You could say it's the molar volume at STP. And it applies to any gas. All right, we're going to wrap it up here with this slide right now. So this is section 7.2, properties of gases and gas laws. Thanks. See you next time.